Good morning, everyone. Today we will study non-homogeneous linear recurrence relation and its solution. So first of all, what is non-homogeneous linear recurrence relation? It is a relation of kth order with constant coefficient which is written as C naught an plus C1 an minus 1 plus C2 an minus 2 plus Ck an minus k equal to Fn. Here C naught, C1, C2, Ck are constants. The relation of this form is called the non-homogeneous linear recurrence relation. Now we know how to find the solution of this homogeneous recurrence relation which we have studied in previous lecture. Now how to find the solution when we have this term on the right hand side. So to find the total solution of non-homogeneous solution, we will find it in two parts. First, we will find the solution of this homogeneous part. Then we will find the particular solution of this part. And the total solution will be homogeneous solution plus particular solution. To obtain the particular solution of this non-homogeneous recurrence relation, we will use trial solution. So if this function fn is of the form b raised to power n, then we will write an equal to a raised to power bn as a trial solution. If fn is of the form which is polynomial of degree k in n, then we will write trial solution as a naught a1, a naught plus a1n plus a2n square plus ak nk. The degree of trial solution and the degree of polynomial is same. If the polynomial is multiplied by bn, then the trial solution is also multiplied by bn. If fn is of the form sin bn or cos bn, then the trial solution will be an equal to a sin bn plus b cos bn. If it is multiplied by bn, means bn sin bn or bn cos bn, then trial solution is also multiplied by bn. So to find the solution of non-homogeneous recurrence relation, we will find the solution in two parts. We will solve homogeneous recurrence relation to find the solution of the homogeneous part, and then we will find the particular solution using trial solution, and the total solution will be homogeneous solution plus particular solution. So there are many techniques to find the particular solution of the recurrence relation, but today we will discuss the method of undetermined coefficients. So how to find the particular solution of the difference equation an minus 4 an minus 1 plus 4 an minus 2 equal to 2 raised to power n. We have studied in previous lecture how to find the characteristic equation of this homogeneous part. So today I am writing it directly. So characteristic equation of given equation is alpha square minus 4 alpha plus 4 equal to 0. Alpha square minus 4 alpha plus 4 is nothing but alpha minus 2 whole square. It means alpha is equal to 2, which is repeated twice. So this characteristic equation has two roots which are equal to 2. Here on the right hand side we have the term of the form 2 raised to power n. Since 2 is a characteristic root of multiplicity 2, the general solution of the general form of particular solution will be an equal to a 2 raised to power n into n square. Here this term n square is due to the multiplicity 2 of the root 2. So this is our trial solution. If we replace n by n minus 1, an minus 1 equal to a 2 raised to power n minus 1 into n minus 1 whole square. If we replace n by n minus 2, an minus 2 is equal to a 2n minus 2 into n minus 2 whole square. If we substitute these values of an minus 1 and an minus 2 in the given recurrence relation, we get a 2n n square minus This is 4. 4 a 2n minus 1 into n minus 1 whole square. The value of a raised to power a n minus 1 plus 4a n minus 2. So 4 a 2n minus 2 into n minus 2 whole square equal to 2 raised to power n. Now take a raised to power 2n common. So inside we have n square here. A raised to power 2n is common. So inside we have 4 and 2 raised to power minus 1 and minus 1 whole square. We have taken a 2 raised to power n common. So inside we have 4, 2 raised to power minus 2 and minus 2 whole square equal to 2 raised to power n. It means take a 2 raised to power n we have taken to be common. So inside we have n square minus 4 into 2 inverse is 2. Open the square, n square plus 1 minus 2n. 4 into 2 raised to power minus 2 is 1. So open this bracket, n square plus 4 minus 4n. And this is 2 raised to power n. 2 raised to power n will cancel on both sides. So we are left with a. And here n square minus 2n square plus n square. It means n square and n square is 2n square and minus 2n square. It will cancel out. Then minus 2 and minus 2n. This is plus 4n. Here we have minus 4n. These will cancel out. Here we have minus 2 and this is plus 4. 4 minus 2 is 2. So this is 2 here. So 2 and this 2 raised to power n and this is 2 raised to power n. This will cancel out. 2a equal to 1 means a equal to half. If we substitute the value of a in our trial solution, we get an equal to 2 raised to power n minus 1 into n square, because a is 1 upon 2 into 2 raised to power n means 2 raised to power n minus 1. One more example. If you find the particular solution of an minus 3an minus 1 plus 2an minus 2 equal to 2n, then in this case the characteristic equation can be written as alpha square minus 3 alpha plus 2 equal to 0. This is easy to calculate because we have learnt how to find the characteristic equation in our previous lecture. If we factorize this characteristic equation, we get alpha minus 1 into alpha minus 2 equal to 0. Means one root is 1, another root is 2. So alpha 1 equal to 1 and alpha 2 equal to 2. Here we have 2 raised to power n. So 1 is not equal to 2, but 2 is equal to 2. So we will consider this root. And this root is of multiplicity 1. Therefore, our trial solution will be an a 2n into n. Earlier, the multiplicity of root was 2. In that case, we had taken n square here. Now the multiplicity is 1. So I have taken n here. If we replace n by n minus 1, a n minus 1, a into 2n minus 1 into n minus 1. If we replace n by n minus 2, a n minus 2, a 2 raised to power n minus 2 into n minus 2. If we substitute the values of an minus 1, an minus 2 in the given recurrence relation, we get a 2n into n minus 3a 2 raised to power n minus 1 into n minus 1, this value, plus 2an minus 2 plus 2a 2n minus 2 into n minus 2, this value equal to 2 raised to power n. If we take a raised to power 2n common, then here we are left with n. This is 3, a is outside, 2 raised to power n is outside, so 2 raised to power minus 1 and minus 1. This is 2, a is outside, 2 raised to power n is outside, so this is 2 raised to power minus 2 into n minus 2 equal to 2 raised to power n. We can cancel 2 raised to power n on both sides because we have here 2 raised to power minus 1. So to simplify it, we will multiply this equation by 2 on both sides. So we get a, if we multiply it by 2, 2n. This is 3. If we multiply it by 2, this is 1 and minus 1. If we multiply it by 2, 2 square into 2 raised to power minus 2. So this is 1, this is n minus 2. and this is already cancelled, and multiply by we are left with 1. I mean, multiplied 1 by 2, so this is 2. So this is 2n minus 3n minus n plus n, cancelled, minus and minus plus 3 minus 2. So 3 minus 2 is 1. So this is a equal to 2. If we substitute it in our trial solution here, so this is an 2 raised to n plus 1 into 2, because 2 into 2n is 2 raised to n plus 1 into n. Now we will do one more example. An plus 5 an minus 1 plus 6 an minus 2 equal to 3n square. In this case, we have a polynomial of degree 2 here. So, the trial solution will be an equal to a1 plus a2n plus a3n square. The degree of trial solution is same as the degree of the polynomial. If we replace n by n minus 1 and then n by n minus 2, for substituting the values of an minus 1 and an minus 2, we get a1 plus a2n plus a3n square in place of an, plus 5 into a1 a2 into n minus 1 plus a3 into n minus 1 whole square in place of an minus 1, plus 6 into a1 plus a2 n minus 2 plus a3 n minus 2 whole square in place of an minus 2. We have replaced n by n minus 1 for an minus 1 and n by n minus 2 for an minus 2. On the right hand side, we have 3n square. If we open the squares and multiply these, then on simplification we get 12a3 n square, means coefficient of n square is 12a3. Let's check here. Coefficient of n square is a3, means 1. Here the coefficient of n square is a3 multiplied by 5. So 5a3, 5 and 1, 6a3. Here coefficient of n square a3, and this is 6a3. 6a3, 6a3, 12a3 n square. Then coefficient of n. So this is a2. Then again here we have 5a2, coefficient of n means 6a2. Then again we have coefficient of n 6a2. 6a2 plus 6a2, 12a2. So minus and minus plus 12a2. Then again the coefficient of n, we will look for the a3 terms. So here we don't have any term. Here we will have the term, if we open the bracket, n square plus 1 minus 2n. So minus 2n means multiplied by 5 minus 10n. Then again here a3 term, n square plus 4 minus 4n. Minus 4n means 24n. 20 minus 24, and here minus 10n, to minus 34 a3. This is the coefficient of n. Here I have written the constant terms. For constant term it is a1. Here we have 5a1 means 6a1. Here we have 6a1 means 12a1. This is 12a1. Then another constant term. Here we have minus a2. This is multiplied by 5 means minus 10a2. Then this is minus 2a2 multiplied by 6, 12a2. So minus 12a2 minus 5a2, 5 not 5, 10a2. So it will be, sorry, minus 5a2 and minus 12a2. So it will be minus 17a2. Then a3 terms. So for a3 terms, here we have n square plus 1 minus 2n. So constant term is plus 1 and this is 5. And again the constant term here is minus for A3 n square plus 4 minus 2n means plus 4. So plus 4, this is 6. 6 fours are 24 and here it was 5. So 29A3 equal to 3n square. Now to calculate the values of A1, A2 and A3, we compare the coefficients of like terms on both sides. Comparing the coefficient of n square on both sides, we get, here it is 12A3, here the coefficient of n square is 3. So 12A3 equal to 3 means A3 equal to 3 upon 12 means 1 upon 4. Coefficient of n, 34A3 minus 12A2. Here we don't have n, so it is 0. Means A3 is 1 upon 4. So 34 upon 4 minus 12A2 equal to 0. Means 12A2 is equal to 34 upon 4, or A2 is equal to 17 upon 2, and this 12 will come in the denominator, 17 upon 24. If we compare the constant term on both sides, 29A3 minus 17A2 plus 12A1 equal to 0. So in place of A3, I write 1 upon 4. In place of A2, we write 17 upon 24. So 29 into 1 upon 4 so minus 17 upon 24 plus 12A1 equal to 0. Means minus 115 upon 24 plus 12A1 equal to 0. By subtracting these two terms, means A1 is equal to 115 upon 288. So substitute the value of A1, A2 and A3 in the trial solution. We get An equal to 115 upon 288 plus 17 upon 24 n plus 1 upon 4 n square. This is the required particular solution of the given non-homogeneous recurrence relation. For one more example, we find the recurrence relation of an plus an minus 1 equal to 3n into 2 raised to power n. Here it is the function of the form 3n into 2n. 3n is a polynomial of degree 1 and it is multiplied by 2n. So it will be polynomial of trial solution will also be polynomial of degree 1 and it will be multiplied by 2n. So an is equal to a1 plus a2n plus 2 raised to power n. Now for a n minus 1, we will replace n by n minus 1 in this trial solution. So if we substitute these values in given relation, we get a1 plus a2n 2 raised to power n plus a1 plus a2 n minus 1 2 raised to power n minus 1. I have replaced n by n minus 1, n by n minus 1. On the right hand side we have 3n into 2 raised to power n. If you open these brackets, a1 2 raised to power n plus a2 n 2 raised to power n plus a1 2 raised to power n minus 1 plus a2 n 2 raised to power n minus 1, and this is minus a2 2 raised to power n minus 1 3n 2 raised to power n. Now collect the like terms together. This is a1 2 raised to power n. This is the term containing a2n 2n. So I have written here a1 2n minus 1. This is a2n 2n minus 1. Here this term is here. Then a minus a2 2n minus 1 equal to 3n 2 raised to power n. So I have written similar terms in one bracket, means, and the coefficients of n 2 raised to power n means multiple of n in one bracket. These are multiples of n, these are not multiple of n. So on the right hand side we have 3n 2 raised to power n. Now to find the coefficients, unknown coefficients a1 and a2 in the trial solution, we will compare the coefficients of like term on both sides. If we compare the coefficient of n 2 raised to power n on both sides, we get Here the coefficient of n2 raised to power n is a2. Here it is a2 2 raised to power minus 1. Coefficient of n 2 raised to power n. a2 2 raised to power minus n. n 2 raised to power n. Coefficient is 3. So 2 inverse means 1 upon 2. If we multiply it by if a2 is 2 inverse is 1 upon 2. So a2 plus 1 upon 2 a2 is 3 by 2 a2. 3 by 2 a2 means 3 a2 equal to 6 by cross multiplication. So it means a2 is equal to 6 upon 3 means 2. If we compare the coefficient of 2 raised to power n on both sides, here we have a1, here we have a1 into 2 raised to power minus 1, here we have a2 into 2 raised to power minus 1. Coefficient of 2 raised to power n, coefficient of 2 raised to power n, coefficient of 2 raised to power n. On the right hand side, we don't have term containing 2 raised to power n, so it is 0 here. So a1 plus a1 upon 2. 2 inverse means 1 upon 2. a1 plus a1 by 2 means 3 by 2 a1. a2 is 2, so 2 into 2 inverse is 1. Shift this to this side, so 3 by 2 a1 equal to 1 means a1 equal to 2 upon 3. So substituting all the values, we get an equal to a1 is 2 by 3 plus a2 is 2 and 2n. So this is the required particular solution of the given recurrence relation. Now we will solve the recurrence relation an plus 6an minus 1 plus 9an minus 2 equal to 3 with the boundary condition a naught equal to 0 and a1 equal to 1. Here the characteristic equation will be alpha square plus 6 alpha plus 9 equal to 0. So this is the square of alpha minus 3 whole square. Sorry, alpha plus 3 whole square. Alpha plus 3 whole square means alpha is equal to minus 3 and minus 3. Minus 3 is a root of this equation which is repeating twice. Means alpha 1 is minus 3, alpha 2 is minus 3. So the homogeneous solution is an equal to a1 plus 2n minus 3 raised to power n. Because minus 3 is repeating twice, so homogeneous solution will be a1 plus a2n into minus 3 raised to power n. And because minus 3 is characteristic root of multiplicity 2, therefore the trial solution will be a3 plus a4n plus a5n square. Now substitute n square term is due to the multiplicity. Now substituting the value of an in the given equation, to substitute the value of a raised to an minus 1, we replace n by n minus 1. To substitute the value of an minus 2, we replace n by n minus 2. Then we get a3 plus a4n plus a5n square plus 6, the 6, a3 plus a4 n minus 1 plus a5 n minus 1 whole square plus 9 a3 plus a4 n minus 2 plus a5 n minus 2 whole square equal to 3. It means if we open the brackets, open the squares, on simplification we get 16a5n square plus 16a4 minus 48a5n plus 16a3 minus 24a4 plus 42a5 equal to 3. I have written all the terms of n square together, all the terms of n together and all the constant terms together after simplification. If we compare the coefficient of n square on both sides, 16a5 is equal to 0. We don't have the term containing n square here. It means a5 equal to 0. Now the coefficient of n, 16a4 minus 48a5. Here we have 0. So 16a4 minus 48a5 equal to 0. a5 is 0 means a4 equal to 0. 16a4 equal to 0 means a4 equal to 0. Now for constant term, 16a3 minus 24a4 plus 42a5 equal to 3. So a4 is 0, a5 is 0 means 16a3 equal to 3. a3 equal to 3 upon 16 means a3 equal to 3 upon an is equal to 3 upon 16, because in the trial solution a4 is 0, a5 is 0, so an is equal to 3 upon 16. Hence, the solution of the given recurrence relation is homogeneous solution plus particular solution. Now, the homogeneous solution is a1 plus a2n minus 3n, this term, and the particular solution is 3 upon 16. Now to find these constant, we use these boundary conditions. For n equal to 0, a0 is 0. For n equal to 1, a1 is 1. So for now using the boundary condition, a0 equal to 0 means n equal to 0. So this is 0, this is a1, this is 0, this is 0, means minus 3 raised by 0 is 1. But this term is 0. Here we have only a1 plus 3 upon 16. It means a1 is minus 3 upon 16. For n equal to 1, we have a1 is 1, a1 plus a2 minus 3 raised by 1 plus 3 upon 16. Now substitute the value of a1 minus 3 upon 16. 1 equal to minus 3 upon 16 plus a2 into minus 3 plus 3 upon 16. On simplification, we get 1 minus 12 upon 16 is equal to minus 3a2. Means a2 is equal to minus 1 upon 12. Hence the required solution is minus 3 upon 16 minus 1 upon 12n into minus 3 upon n plus 3 upon 16. One more question. How to solve the recurrence relation an minus 4 an minus 1 plus 4 an minus 2 equal to n plus what? 2 raised to n with these boundary conditions. We know that the characteristic equation is alpha square minus 4 alpha plus 4. This is nothing but alpha minus 2 whole square. Means the root of equation is 2, which is repeating twice. Alpha 1 equal to alpha 2 equal to 2. Therefore, homogeneous solution will be a1n plus a2 into 2 raised by n. Because 2 is a characteristic root of multiplicity 2 and n plus 1 is a polynomial of degree 1. Therefore, we write an equal to n square a3n plus a4 2 raised by n. See, this is a polynomial of degree 1. So that's why I have written a3n plus a4. It is multiplied by 2n. So it is multiplied by 2n. Because 2 is of multiplicity 2, therefore n square. This term is multiplied when the multiplicity is 2. Now replacing n by n minus 1 and n by n minus 2 for substituting the value in the given recurrence relation, we get n square a3n plus a4 into 2 raised by n minus, this is 4. For this value an minus 1, replace n by n minus 1 and minus 1 whole square a3 n minus 1 plus a4 plus 2n minus 1 plus 4 an minus 2 plus 4, replace n by n minus 2 and minus 2 whole square a3 n minus 2 plus a4 2 raised by n minus 2 equal to n plus 1 into 2 raised by n. Now simplify this equation. On simplification, Open all the square brackets, open all the brackets. On simplification, we will get a3, 6 and minus 6, 2 raised to n plus 2, a raised to 4, 2n plus n plus 1, 2n. It means 6a3n, 2 raised to n, and minus 6a3 plus 2a4, 2 raised to n equal to n2n plus 2 raised to n. If we compare the like terms on both sides, we get 6a3 coefficient of n raised to 2n. 6a3 is equal to 1, coefficient of this term 1. Minus 6a3 plus 2a4 equal to 1, coefficient of 2 raised to n. So it means a3 equal to 1 upon 6. Substitute a3 equal to 1 upon 6 here. This is minus 1. If we shift to this side, 2a4 equal to 2 means a4 equal to 1. Therefore, an is equal to n square plus n upon 6 plus 1 2 raised to power n. This is the particular solution and this is the homogeneous solution. The total solution will be homogeneous solution plus particular solution, means a1n plus a2 2 raised to n plus n square n by 6 plus 1 2 raised to power n. Now to find these constants, we substitute these boundary conditions. a0 is 1, a1 is 2, a2 is 3. Once for n equal to 0, it is 1. For n equal to 1, a1 is 2. For n equal to 2, a2 is 3. For a0, n equal to 0, this term is 0. And we are left with a2. 2 raised to 0 is 1. This term is also 0. So a2 is equal to 1. For a1 equal to 2 means n equal to 1. So this is 2 plus a1 plus a2, 2, 1 by 6 plus 1, 2. So it means 2 is common everywhere. So it is 1, a1, a2 is 1. So a1 plus 1 and 1 by 6 plus 1, 7 by 6. Simplify it, a1 equal to minus 7 by 6. So the final solution will be, general solution of recurrence relation will be minus 7 by 6n plus 1 2 raised to power n plus n square n by 6 plus 1 2 raised to power n. Thank you.